general relativity, step by step. I've been trying to evaluate this term here, which is the expression for the relative tidal acceleration caused by the passage of a gravitational wave. And we've shown that it's equal to this thing here, minus the Riemann-Christoffel tensor contracted with the separation vector n with index nu. And then we used the linear approximation, the linearization, and of course the transverse gauge condition to simplify the Riemann-Christoffel tensor down to this form here. What I'm going to do now is to evaluate this beast in our coordinate system. Sometimes I'll write 0 for the time coordinates, and sometimes I'll write t down. So yeah, see, I've written t, and it's sort of a mixture. So it's di by di t of Christoffel symbol alpha t nu, where alpha and nu at the moment are free variables. Okay, what was my metric tensor? Was equal to the flat space Minkowski metric plus something small times this rather special matrix here, alpha, beta, beta minus alpha. I got it right that time. I think I've written it down wrong nearly every time. That's small, e to the I minus omega t. I've got to pause every time there because I can never remember which way around I did it. Z. Okay, so it's got a time component and a z component. So let's evaluate. What I'm going to do now is to evaluate the Christoffel symbol with a time in one downstairs position, nu there, following that metric there. Well, it's a half g. Actually, why don't I just do it in one go? It's eta because I'm considering only flat space. I'm considering only the linear approximation, I'm sorry. Alpha times pi. I'm going to write it like this and then I'm going to edit it. Di g da da by di x da plus di g do do by di x do minus di g blah blah by di x blah. The pi sums with the first place, the second place, the bottom place. What have we got left? We've got t and nu. So it's t and nu, t and nu, t and nu. You see how much easier this makes our lives? Because straight away I can get my red pen out, which is here, and I can cancel that term there. Why? Because the first row of the perturbation is 0 in the first column, I guess, and there's a time there, so that means that this row and this row are operating, and they're all zeros. That's 0 as well because we've got a time there. Oh, and that's 0. So what on earth's going on? Hang on. What have I done wrong here? Oh dear, that was yes, I've got that now. You see, you've got to write pi. Let me go back to black here. Pi in the first place, pi in the second place. We've got t and nu, and I've got t and nu in the same order. So I need to scribble. I'll zoom in a bit more if I can. Yeah, there we go. You see, it's t and nu. It should be t and nu. There we are. So now I can do some proper cancelling. Let me do it properly this time. Go back to red. Oh, that is becoming a pain. Go back to red. This is 0 because it's that row there. Haha, this one isn't because it's a nu and a pi there. That one there is 0 because it's a row. And here we've got something altogether different. Let me go back to black and I'll rewrite this expression here. We've got a half eta, which we know to be diagonal, so that's alpha alpha. That tells me that pi must be equal to alpha because all the other terms are off diagonal and they drop out. This first term and this third term have dropped out, so we've got di g nu alpha by di t. Yeah, that's right, isn't it? That's right, isn't it? And we know that alpha cannot be equal to 0 because if alpha equals 0, we've got a 0 term here. Oh, well, that's quite nice, isn't it? So let me rewrite what we want, which is this thing here. We need di by di t of the Christoffel symbol with time downstairs, alpha and nu, which is plus 1, because we know that alpha is not equal to 0, so we're in 1, 2, 3, one of those coordinates there. Di by di t of g nu alpha. There we go. Oh, and I've got a half as well, times a half. Equals 1/2 di 2 by di t squared, acting on this thing here, because we're only considering derivatives, so I can ignore him. We can just work on that. So I'll write it out. I've got my half's there. I've got my two derivatives. The plus 1, why is it plus 1? It's because we're considering only spatial components. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, alpha, beta, beta minus, oops, that's a gamma, e to the I minus omega t plus omega z. Aha, well that's nice, isn't it? Where that line there is, what are we considering? We're considering the this component here of the Riemann-Christoffel curvature tensor, which is this one, alpha O nu O, minus our alpha t nu t equals this thing here. All right. Well, it's still quite well. It's not as bad as it looks because the second derivatives are dead easy. Well, we'll come to that. I'm going to stop here because I'm going to cock it up if I carry on too long. So we've got a nice expression here for minus r alpha t nu t, or sometimes I've been writing it with 0 nu 0 there. Okay, well, we'll interpret that in the next screencast. Stop there. Stop.